In this video, I will discuss some electrostatics problems from previous year's question papers of IIT JEE. This is the first question. A long, hollow, conducting cylinder is kept coaxially inside another long, hollow, conducting cylinder of larger radius. Both the cylinders are initially electrically neutral. Option A. A potential difference appears between the two cylinders when a charge density is given to the inner cylinder. Option B. A potential difference appears between the two cylinders when a charge density is given to the outer cylinder. Option C. No potential difference appears between the two cylinders when a uniform line charge is kept along the axis of the cylinder. Option D. No potential difference appears between the two cylinders when same charge density is given to both the cylinders. You can pause the video and attempt this question. Here is the solution. So let us analyze the options individually. Option A, when a charge density is given to the inner cylinder. So when a charge is given to the inner cylinder, it's a conducting cylinder. So the charge will go to the outer surface. This is a standard concept because the electric field inside the metal, which is making this wall of this cylindrical shell, should be zero. So the charge should go outside. If it resides on the inner surface, then there will be electric field in this conducting medium, which is not allowed. So the charge inside should be zero and all the charge should go to the outer surface. So let that charge be sigma, and this sigma will produce an electric field and it will induce a same amount of charge on the outer cylinder, so that the electric field coming out of this surface goes and ends here, because again there is a conducting layer here where there cannot be any electric field. So whatever electric field comes out of this surface should end on this surface. And since the outer cylindrical shell is electrically neutral, there is no charge, so there should be a surface of the plus sigma on the outer surface of the outer cylinder. So in this configuration there will be an electric field between the two cylindrical shells. Since there is an electric field, there will be a potential difference between these two inner and outer cylinders. So the option says, A says there is a potential difference, so option A is the correct one. Let us analyze the other options also for the sake of completeness. Option B says a potential difference appears between two cylinders when the outer charge is given to the outer cylinder. When charge is given to the outer cylinder, the charge will get distributed on the outer surface. For the same reason, there cannot be any electric field within this conducting material. So on the inner surface there will be zero charge, so there will be zero charge on the inner cylinder also. So here in this case the electric field between the two cylindrical shells is zero, so there is no potential difference between the two. But option B says there is a potential difference between the two, so option B is not correct. Option C, no potential difference appears between the two cylinders when uniform line charge is kept along the axis of the surface. When uniform line charge is kept along the surface, it will induce a charge on the inner surface of the inner cylinder, because let us assume this lambda is positive, so it will produce an electric field, and the electric field line should go and hit this inner surface of the inner cylinder. And since there is no electric field within the conductor of this inner shell, all the surface negative charge should be on the inner surface. So the outer surface will have plus sigma, so the net charge on this inner cylinder is zero, and this will induce a minus sigma on the inner surface of the outer cylinder, and there will be plus sigma on the outer surface of the outer cylinder. So there will be electric field between these two cylinders, and so there will be a potential difference. So option C is also not correct. Option D, no potential difference appears when same charge density is given to both the cylinders. When a surface charge density of sigma is given to the inner cylinder, will go to the outer surface, and this will induce a minus sigma on the inner surface of the outer cylinder, and there will be a surface charge density of 2 sigma on the outer surface of the outer cylinder, because the net charge density is 0. So here in this case there is a potential difference between there is electric field between the inner cylinder and the outer cylinder, so there will be a potential difference. So option D is also not correct. So the correct option is option E for this question. Let's move to the next question. Consider neutral conducting sphere. A positive point charge is placed outside the sphere. The net charge on the sphere is then option A, negative and distributed uniformly over the surface of the sphere. B, negative and appears only at a point on the sphere closest to the point charge. C, negative and distributed non-uniformly over the entire surface. Option D, 0. You can pause and attempt this question. So when a positive charge is brought near a conducting sphere which is neutral, the electric field lines coming out of this positive charge will end here. So there will be a negative charge induced on this surface, and since initially the charge on this sphere is 0 because it's neutral, positive charge will appear on the other side. So there will be charge separation, and all the electric flux lines which come out of this plus Q will go and terminate on the negative surface charge of this sphere. But the net charge on this conducting sphere will be 0 because it's isolated and initially it was neutral. So the correct option is option D. Let's move to the next question. A spherical portion has been removed from a solid sphere having charge distributed uniformly in its volume as shown in the figure. The electric field inside the emptied spaces. 4 options are given. You can pause and attempt this question. So the sphere with a cavity, where the sphere has got with a cavity has got a uniform charge density, say rho, is equivalent to a sphere without cavity, where the charge density is uniform at 0, plus a sphere corresponding to the volume of this cavity, which has got a volume density of minus rho. So when we combine the effect of these two spheres, we get the equivalent effect of a sphere with a cavity. So to find the electric field due to this sphere with a cavity, we can find the electric field due to the combination of this bigger sphere with charge density rho and a smaller sphere due to charge density minus rho. This is possible because of superposition principle, which is applicable for electric field calculation. So to find the electric field due to a uniformly volume charge distribution, we'll use a standard result, that is electric field is rho by 3 epsilon naught into the r vector. So electric field at a point P is electric field due to this plus rho at this point P, and electric field due to this minus rho distribution at this point P. So electric field due to the plus rho is, using this result, rho by 3 epsilon naught into the position vector, which is the vector joining the center of the sphere to the point P. So it is this vector, and the electric field due to the minus rho will be minus rho by 3 epsilon naught into C2P. So we can absorb the minus sign in C2P and write it as PC2. So now we have to add the vectors C1P and PC2. So C1P is this vector plus PC2. So the resultant will be this vector, which is joining the centers of the two spheres. So it is C1, C2. So this is independent of the position of the point P. So at any point P inside the cavity, the electric field value is given by this, which is independent of the position of the point P. So the electric field inside the cavity is uniform. So the option B is the correct one. Option B says the electric field is non-zero and uniform inside the cavity. Let's move to the next question. Positive and negative point charges of equal magnitude are kept at 0, 0, a by 2 and 0, 0, minus a by 2 respectively. The work done by the electric field when another positive point charge is moved from minus a 0, 0 to 0, a 0. 4 options are given. You can pause and attempt this question. So here is the solution. So it's a problem where we have to visualize the situation in 3 dimensions because all the 3 coordinates are involved, x, y and z. So to draw the figure properly, so the x-axis is horizontal and y-axis is vertical along the plane of this paper, and z-axis is coming out of the plane of the paper, and the charges, positive and negative charge kept at z equal to a by 2 and z equal to minus a by 2. So it is these two locations, positive charge at z equal to a by 2 and z equal to minus a by 2 we have negative charge, and a positive charge is moved from the point minus a, x equal to minus a, that is this point P, to y equal to a, that is this point Q. So work done in moving a charge from one point to another point is the value of the charge into the potential difference between these 2 points. So if you know the potential at the point P and the potential at point Q due to the charge distribution, then we can find the work done in moving the charge from P to Q. Potential at point P is due to the 2 charges plus Q and minus Q. It's a point charge, so the formula is simple. It's K into the charge divided by the distance, where K is 1 by 4 pi epsilon naught. So this charge Q, so let this distance be D, the distance from P to the point charge, and the charge minus Q is also at the same distance D. We have to visualize in 3D. So this distance is also D. So K minus Q by D, where D square is A square plus A by 2 square. So this is by Pythagoras theorem. Similarly, potential at point Q due to the 2 charges will be KQ by D, where D is the distance, the same distance, just in the vertical plane, and K minus Q by D. So the value of potentials at point P and Q are same. This we can also understand by symmetry argument, because both P and Q are equidistant from the charges plus Q and minus Q. So the potential at point P and point Q should be same, because it depends on the charge value of the distance, how far it is. So the work done in moving from P to Q is Vp minus Pq, that is 0. So the work done is 0. The correct option is option C. This is the next question. Consider a system of 3 charges, q by 3, q by 3 and minus 2 by 3 into q at points A, B and C respectively as shown in the figure. Take O to be the center of the circle of radius r and angle CEB is 60. Option A, the electric field at point O is this expression directed along negative x. Option B, the potential energy of the system is 0. Option C, the magnitude of force between the charges at C and B is this expression. Option D, the potential at point O is this expression. You can pause and attempt this question. So the charges plus q by 3 and plus q by 3 are kept at the points A and B, and a charge minus 2 by 3 q is kept at point C. So the option A, we have to find the electric field at point O, that is the origin, that is the center of the circle. The electric field due to plus q by 3 at A and B will cancel each other because they are diametrically opposite, and electric field is force between a unit positive charge kept at O and the charge at A and B. So electric field due to A and B will cancel, so there will be electric field contribution only due to minus 2 by 3 q. So that is 1 by 4 pi epsilon naught, the charge value divided by the distance square. So this is q divided by 6 pi epsilon naught r square, and the direction is minus x hat. The force on a unit positive charge kept at origin will be towards left because it will attract this unit positive charge. So option A says the electric field is 1 by 8 and it's positive. Now the direction is negative x-axis, the direction is correct, but the magnitude is 1 by 8, but here we are getting 1 by 6. So option A is not correct. Option B, we have to find the potential energy of the system. Potential of the system is potential of all the interactions. It is K into the charge, product of the charges divided by the distance. So here you have 3 interactions. One is the interaction between the charges A and B, and the second one is the interaction between the charges at B and C, and there is a third interaction between the charges at C and A. So there will be 3 interactions in this system, So there will be 3 terms in the electrostatic potential energy calculation. So K is 1 by 4 pi epsilon naught, that's commonly kept outside, into the product for the charges, Q by 3 squared over the distance between A and B, that is 2r, and minus 2 by 3Q into Q by 3, and the distance between them is root 3r. This we can get by Pythagoras theorem. Hypotenuse is 2r, so hypotenuse square is 4r square minus r square, so it's 3 times r square. Square root of that is root 3 into r. So distance BC is root 3 into r, and the third interaction minus 2q by 3 and q by 3 at a distance of r. So taking q square by r commonly outside, we can get these numbers. So it's not cancelling, so it's not equal to 0. Option B says the net potential energy is 0, so which is not true. Option C, the force between the charges at B and C. This is given by simple Coulomb's law, 1 by 4 pi epsilon naught, product of the charges divided by the distance square. So that is turning out to be 1 by 54 pi epsilon naught q square by r square. 1 by 54. So C is the correct option. So let's check D also. We have to find the potential at origin O. Potential is 1 by 4 pi epsilon naught into charge by distance. So the potential will be due to the 3 charges. So q by 3 charges at the same distance of r, so it is twice of that, and then minus 2 q by 3 is also at a distance r. So it is equal to 0, but they are given an expression which is not true. So the only correct option is option C. This is the next question. A disk of radius a by 4 having uniformly distributed charge of 6 coulomb is placed in xy plane with its center at minus a by 2, 0, 0. That is this one. A rod of length carrying uniformly distributed charge of 8 coulombs is placed on the x-axis from x equal to a by 4 to phi a by 4. That is this one. And 2 point charges minus 7 coulomb and 3 coulombs are placed at a by 4, minus a by 4, 0, and minus 3 by 4, 3 by 4, and 0 respectively. Consider a cubical surface formed by 6 surfaces, x plus or minus a by 2, y plus or minus a by 2, z plus or minus a by 2. The electric flux through this cubical surface is. You can pause and attempt this question. So this is the location of the cube. So we can get the flux passing through this cube by applying Gauss's law. Gauss law says the flux coming out of a closed surface is the net charge inside divided by epsilon naught. So you have to find the total charge which is present inside the chosen Gaussian surface. So this is a Gaussian surface. So the charge of this disk, which is totally 6 coulomb, so half of it is inside. So the charge contribution from this disk is half of 6. And this rod, the length of the rod is A, and it's starting from A by 4 and going up to phi A by 4. So this length is A, and this size of this cube is A by 2. It's located at plus A by 2. So the amount of line charge which is present is 1/4 of it. So 1/4 of 8, that is the charge present inside due to this line charge. And there is 1 point charge at minus C, which is at minus A by 4, y equal to minus A by 4, and x equal to plus A by 4. So it is inside this cube, and the charge of plus 3 is here. The coordinates are being given. So from that we can see that the charge is lying outside at a distance of 3a by 4. So only this point charge of minus 7 is present inside. So if we total this charge which are present inside, that's 3 plus 2 minus 7 is minus 2. So minus 2 by epsilon naught is the flux coming out of this surface. So the correct option is option A. This is the next question. Three concentric metallic spherical shells of radii R2, R3, R are given charges Q1, Q2, Q3 respectively. It is found that the surface charge densities on the outer surfaces of shell are equal. Then the ratio of the charges given to the shells Q1 is to Q2 is to Q3 is. You can pause and attempt this question. Here is the solution. So the charge Q1 which is given to the innermost spherical shell, it will reside on the outer surface because the electric field inside the conducting material should be 0. So if there is some charge present inside the inner surface of the inner shell, then there will be some electric field passing through this material of the conducting shell, which is not allowed. So all the charge will reside on the outer surface of the inner shell. So this will induce a charge of minus Q1 on the inner surface of the middle shell, because all the electric field lines which are coming out of this inner shell should terminate on this inner surface of the middle shell, as there cannot be any electric field on the material of this second shell, as it's made of a good conductor. And the net charge on the middle shell is Q2, so the charge on the outer surface should be Q1 plus Q2, and this will induce a charge of minus Q1 minus Q2 on the inner surface of the outermost shell, and the net charge on the outermost shell is Q3, so the charge on the outer surface of the outer shell should be Q1 plus Q2 plus Q3. So the charge distribution is. So once we know how the charge distribution, we can find the surface charge density of the outer surface of the shell. So the surface density of the outer surface of the first shell, the inner shell, is Q1 by 4 pi r square, and for the outer surface of the second shell, middle shell, is Q1 plus Q2 divided by 4 pi, its radius square, that is 2r square, and for the outermost shell it's Q1 plus Q2 plus Q3 divided by 4 pi, its radius square, that is 3r square. So 4 pi can be cancelled, r square can be cancelled, so we get Q1 equal to Q1 plus Q2 by 4, and that's equal to Q1 plus Q2 plus Q3 by 9. So from this equality we get 3Q1 equal to Q2, so Q2 is thrice Q1, and using this equality we get this one 5 times Q1 plus Q2 equal to 4Q3, and Q2 can be written in terms of Q1 using this one. So from this we get Q3 is 5 times Q1, so Q1 is to Q2 is to Q3 is 1 is to 3 is to 5. So the correct option is option B. This is the next question. Under the influence of Coulomb field of charge plus capital Q, charge minus Q is moving around in an elliptical orbit. Find out the correct statements. Option A, the angular momentum for charge minus Q is constant. Option B, the linear momentum of charge minus Q is constant. Angular velocity is constant. Linear speed is constant. You can pause and attempt this question. This motion is similar to a planetary motion of a planet around the sun. So whatever concept is applicable in that system is applicable here also. There is gravitational force that exists between the sun and the planet. Here is electrostatic force of attraction between two opposite charges. So there angular momentum is conserved. Other things won't be conserved. Linear momentum won't be conserved because the direction is changing, direction of velocity is changing. Angular velocity is not constant because of elliptical orbit. Linear speed is also not constant because the direction of the speed is velocity is changing. So option A is the correct one.